All right, time to wrap up our lecture and think about what our takeaways are and the parts that are still a little bit muddy to us. It's very important that you clarify that for yourself so that you can now honestly answer the questions on the bottom, which I will move on to now. So let's look at those and let's really understand these, because this will be your bread and butter for the rest of this class and for exams and so on. So it's so important that we really, really honestly answer these questions correctly or these checkpoints correctly. So the first thing I need to understand is that I can really make a virtual cut anywhere along the structure to find the forces at that location where I cut. So it is important that we understand that it's really any location. And the reason that I'm doing that is because I want to find the values for the internal forces at that particular location. That is technically a conclusion that comes from the last lecture, but it's so important before we discuss what we discussed here today about the diagrams. Because without that, we wouldn't even be able to start our diagram drawings. But that takes us directly into the next checkpoint here, for which we understand that the internal forces really are present at any location, right? Anywhere along the longitudinal axis of the structural element, if you will. That is important to understand so that you really do not get confused between why did we calculate at a particular location before and why are we now drawing diagrams. We only did that for practice. So the previous lectures were really for practice. Really, we want to know how the internal forces act at any location along the member axis. And therefore, we are able to graph these internal forces now. And why do we do that? Because we want to use the graphing methods to represent the numerical values that exist anywhere and everywhere along the longitudinal axis. So please understand that we're really doing this so that we, in one concise graph, have everything in front of us so that we have easy access to all the values that we need. And so what's really important for you is that you can actually use these graphical methods to completely display all the internal forces in any structure. In this case, only for structures that carry concentrated loads. That's what we focused on in this class. In one of our future classes, we will of course expand that to distributed forces and other structural systems. But for now, you can, for easy structures, understand that, and you know how to apply these methods for concentrated loads. All right, so therefore we are now familiar with all the aspects that must be displayed, and let me explain what all the aspects means in this context when we want to display a professional internal force diagram. And what I mean by that is the identifier for one, so normal force, shear force, moment. Then you also need to include the unit in square brackets. You need to include the significant values, right? We talked about that. And you have to identify if an area is in compression or in tension, so plus or minus. And you have to shade the area that is relevant. And all these aspects that we talked about in today's lecture. So you need to be familiar with that, because if you violate any one of those, if you forget any of these, you would not properly communicate in an engineering sense what your values are or what they relate to, and therefore you would have to lose some points on an exam, for example. And in the real world, worst case scenario, somebody doesn't understand what you're talking about. So it's important that you actually include those. All right, and then last but not least, it's very important that we understand that we can mathematically relate the internal bending moment to the shear force. And this can go to much higher levels than what we talked about today. And we will actually talk more about this in the future in this class, but this goes way beyond the purpose of this class. Engineers deal with this a lot later on for different engineering designs. Please remember, though, for now, that we introduced the concept that the shear force is really dm dx. So it's the derivative of the moment. Likewise, we also learned that the load case, which we call W, is equal to the negative of dv dx. We actually had the negative on the other side, but you find it in different textbooks one way or the other, either minus here or the minus here. It means the same thing. However, I hope we truly understand this after this lecture. At least I could visually convince you of that, and you can convince you further through the following homework. But this definitely summarizes our lecture, and we are now happy to study the homework and can take a look at the upcoming problems on the next page. Okay, so here we are at your favorite page, the homework page, and let's take a look at our 6 problems that now relate to internal force diagrams for concentrated forces. You can see that each of these problems have only concentrated forces. And the first one here is a simply supported beam with just 2 forces at specific distances. So this should be a walk in the park after we showed you the first example in this lecture. It's pretty much analogous to that, and I'm sure you are able to solve this, so I don't need to tell you much more here. Let me take you to the next problem. Here you have a similar scenario, but now you also deal with horizontal components. And please pay close attention to drawing the normal force diagram for this particular problem. That's the learning experience we're trying to provide here. But that is all we need to discuss for this problem. Let's go to problem C. Now it will become a little bit interesting. We touched upon the moment here, but we didn't fully explain that in the lecture on purpose so that you can expose yourself to this and really challenge yourself to find the shear force and the moment diagram. Let me tell you right away that the normal diagram for this is 0. And you might think, if the normal is 0, then the shear force is 0 as well. But that is not true, because you will actually end up with support reactions in the vertical direction due to the imbalance of these moments. If you are in the category where M2 is equal to M1, then you have a very special scenario, but you would have to explain why that is not solvable, or rather said, why it's 0 in that case. But I think I already gave that away. But other than that, there's nothing I can help you here with that problem, besides that you have to use it to apply your own individual numbers. Let's move on to the next one. And let's take a look at this cantilever beam here. So here we have a cantilever beam, which of course we didn't discuss today, but it has been discussed in other lectures, at least how we find support reactions. You know how to do that. And we discussed today how to find internal forces. Keep in mind that for internal forces, you can always release either the left side or the right side. And maybe, therefore, this is a very nice, easy, quick problem for you if you already understand how that all works. Because maybe you get away without even calculating support reactions. Or maybe you can use the support reactions to validate your results. But this is a learning experience we want you to go through. So I wish you good luck with that problem. And I move on to the next one, where now we have another cantilever that's supported on the right side in this case. So it feels maybe more natural to release the left side. For some reason, students always start cutting the left side, but I have to convince them in the classroom that it is the same. If you cut the left side or the right side, you will always find the same type of force at that particular location. But you have to draw the internal force diagrams anywhere, so you have to find it everywhere along the member. And I'm pretty sure with all the practice you get from the previous problems, that will be a walk in the park for you. Just note that here now we have a moment. And yes, we want you to really work your way through those. And we are not trying to spoon feed every information to you here, although some people might argue that I do that too much in my lectures. But you have all the tools, I think, from the lecture that you can use to solve this. But sometimes students tell me that it's too difficult. And my response to that is, we are engineers. We want to solve difficult problems, not easy problems, right? So if we would give you problems that you already know how to solve, what would be the point? So the goal obviously is to learn something, and we do that through these problems. Here I have a last cantilever for you, where you now also have to include the normal force diagram so that you can get through that learning experience as well. But that concludes the homework assignment for this lecture, or from this lecture, and we are now ready to solve these problems for concentrated forces. It is good if you complete this before you move on to the next level or the next lecture, because in our next lecture we will actually extend our knowledge and put distributed forces on the systems, and we will see what impact that will have on the internal force diagrams. But for now, you have everything you need to solve these 6 problems and hopefully other ones as well that might cross your way in exams or quizzes. I wish you good luck studying the material. I see you in the next lecture. Until then, stay safe.